Okay, welcome everyone to the afternoon session of today's talks. The first speaker for the afternoon is going to be Diptiman from the Indian Institute of Science, who will tell us about kinetically constrained model showing Hilbert space fragments.
So first of all, let me thank the organizers for inviting me to give this talk. I've given this talk in a few places before, so in case you have heard it before, my apologies. So this work is done with Srimoy Aditya, who was a PhD student. She's now a postdoc in Cologne University. Maitri Ganguly, who was a master's student and is now a PhD student in the University of Illinois, Urbana-Champaign. And Deepak Dhar, who is probably known to most of you, who is currently a faculty here in ICTS. So this is about certain models which show Hilbert space fragmentation. So there was a very nice introduction to this and related issues like eigenstate thermalization hypothesis by Sergej in the morning. So I'll go through some of those things again, but very quickly, because I really want to get onto the models that we studied. So the outline of the talk is as follows. So as I said, there'll be a brief introduction to thermalization, and then I'll talk about Hilbert space fragmentation and specifically two kinds of Hilbert space fragmentation, strong and weak, and then discuss some models using showing Hilbert space fragmentation. And then I'll discuss how we studied these models. So there's a very important concept called root states or irreducible strings. So these are configurations which label the different fragments. So each fragment has a unique root state. And so I'll describe how you find the root states for the different fragments. Then how do you count the number of fragments and what are the sizes of the different fragments? And then some signatures of Hilbert space fragmentation. So there are signatures both static and dynamic. So static signatures are things like half-chain entanglement between two halves of a system, energy level spacings. And then there are dynamic signatures which are autocorrelation functions and Loschmidt echo. Okay, so first a very brief introduction to thermalization. So this was done very beautifully by Sergej in the morning. So I'll go through this fairly quickly. So, it's been believed for a long time that many body local quantum systems which are not integrable will eventually thermalize given an arbitrary initial state. This is supposed to be true even if the system is isolated. So it's not coupled to a bath. So to make this more precise, suppose there's a system, large system S, and we divide it into two parts. There's an A part, which we are interested in, and then the rest of the system, B. And we'll assume B is much bigger than A. So if it's a lattice system, the number of sites in B is much bigger than the number of sites in A. Then one statement of ETH, which goes back to Strednicki in 1994, is that if you consider a single eigenstate with some energy E of the Hamiltonian, now you have to assume that you're taking a typical state. So it should not be near the maximum or the minimum. So it should not be close to the ground state or the most excited state, somewhere in between, with some energy E. And then you consider the Hamiltonian of the system which is restricted to A. So let me call that H of A. So it only has couplings in that region A. And you define the expectation value of the Hamiltonian, this Hamiltonian HA, at time t equal to 0 as just the expected value of this. Then you evolve this in time using H of A. Now, since you're evolving using H of A, this expected value of the energy will not change with time. So you compute the initial reduced density matrix by summing over all the states of the bigger part of the system, B, and then you time evolve rho of A using this equation. So notice that there's nothing else. There are no dissipation or any other terms in this evolution. And then, of course, as I said, this is conserved in time. Then the ETH states that the long-term average of this rho of A, which is defined in this way. So you calculate rho of A, there's an integral d tau missing in this expression. Average over a very long time will be just the same as what one expects for a thermal ensemble corresponding to some temperature T, which is given below. And so I'll describe that. So this is just corresponding to that beta that Sergej described in his talk. So if the eigenvalues and eigenstates of HA are denoted by EJ and psi j, and O is some arbitrary local operator, so it's local within A, so involves only a few sites in A. Then you calculate this trace of this rho A infinity of this local operator O. This should be equal to this for some beta. And this beta is fixed self-consistently by the condition that the expression value of E of A is this Ej e to the power minus beta Ej divided by Z. So there's a 1 by Z missing there. Okay, so over the years, we know that there are at least 4 cases where ETH is not valid. So one case is where the Hamiltonian is integrable, because then there are conserved quantities and the system anyway breaks up into disconnected sectors corresponding to different eigenvalues of these conserved quantities. So for example, if you have a magnetic system where the total spin in some direction is conserved, then the states of the system break up into different sectors corresponding to different values of the conserved quantity. And then it's clear that you'll get quite different values of this trace rho O depending on which sector the initial state lies in. So that's clearly a case where ETH will not work. The second case is where there's many body localization. So here the system gets localized typically in a relatively small region of the Fock space, and thermalization can break down because it's not able to explore the entire Fock space. Now this is actually in some sense the hardest case to study because it requires both in disorder and interactions. Then there is these quantum many-body scars. So these are highly atypical eigenstates. Typically, they have low entanglement entropy between 2 parts of the system. Sometimes they are exactly in the middle of the spectrum if there's some symmetry between E and minus E. So if there's an initial state which has a large overlap with some of the scar states, we'll see it will not thermalize for a very long time because the effects of the scar state will persist forever. Now, the thing is, typically, all the cases known of scars are where the number of scars is very small compared to the total Hilbert space. And so, these really don't have any thermodynamic significance if you start with an arbitrary initial state. But if you happen to start with a state which is close to a scar state, you'll definitely see that it's not thermalizing for a very long time. Finally, there's Hilbert space fragmentation, which is what I'll talk about. So in this case, the Hilbert space breaks up into exponentially large number of disconnected sectors. And the interesting thing is that this happens even if there are no obvious conserved quantities. And so again, the long-term behavior will depend on which fragment the initial state lies in. So this has been studied for several years. And these are some of the pioneering papers, including a paper by Sergej. Very briefly, let me show you an experimental paper showing this Hilbert space fragmentation. So in this paper, they studied a 2-dimensional tilted Bose-Hubbard model with about 200 bosonic atoms. So there is this hopping between nearest neighbors. It's a 2-dimensional system. Then there's a Hubbard U. And there's a tilted field. So if you think about this, I and J are the coordinates of a point in 2 dimensions. And so this is like something which is tilted at 45 degrees. So of course, the number of particles is conserved. That's easy to see. But if this Hubbard U and this delta are exactly equal, and they're both much bigger than the hopping amplitude, you can see that there's another conserved quantity, which is the sum over U at delta at different sites. Okay? So in the experiment, these were the parameters that were taken. And so this is the important parameter. This is the time which is given by 1 over j 10 milliseconds. And so they found that certain states don't thermalize for a time which is much longer than that. And that is like a signature of Hilbert space fragmentation. So what they actually studied is the following. So they took different initial states. So this is a checkerboard pattern where you have particles, either you have 1 particle or 0 particles. And they fill up this region like a chessboard. This second one is also like that, but here the unit cells are bigger, and the various other patterns. So in each of these cases, so let's say you start with this state 1, you find that there's this imbalance which persists for a long time. And notice that in terms of that tau, 1 over j, this persists for up to at least 10 tau. So what is the imbalance? So the imbalance is basically the relative numbers of particles in the odd and even sublattices. So it starts from 1, and then if it was a typical thermal system, this will eventually go to 0. You'll have equal number of particles on the 2 sublattices. But you find that that doesn't happen for a fairly long time. So this is one of the experiments which showed Hilbert space fragmentation. So I should have said that this model is known to be non-integrable. So that's That's why seeing this pattern persist for a very long time is strange property of this model related to fragmentation. Okay, so now let me actually talk about the specific models of Hilbert space fragmentation. So all the known models of Hilbert space fragmentation have some kind of constraints on the kinetics. Okay. So we'll consider some one-dimensional time-bending models where the hopping between two neighboring sites, j and j plus 1, depends on the occupations of their neighboring sites, j minus 1 and j plus 2. So it basically has 4 site terms in the Hamiltonian. Now you can have many possibilities. You can have hopping between these two if these two are empty, the neighboring ones. You can have hopping between these two if the neighboring ones, one is occupied, one is empty, or the other way. Or you can have hoppings between the neighboring sites are both filled and so on. So I like this cartoon picture. It's taken from this paper. And all the processes I'm going to talk about are some variant of these different processes. Okay, so now let me, as an introduction, let me talk about a model which has been studied extensively. It's kind of like the Ising model of Hilbert space fragmentation. And these are some of the papers in which it was first studied. So this is a case where, again, there are four side terms in the Hamiltonian. And the rule is that only the first and fourth processes are allowed. In other words, you can hop between two sites, provided the neighboring sites are either both empty or both occupied. It looks very artificial, but in the next slide, I'll show you a simple model from which this arises in a particular limit. So if you want this as an explicit term in the Hamiltonian, it looks like this. So you can see if nj minus 1 and nj plus 2, these two sites are both empty or both occupied, then this is 1, and then you can have hopping between the two sites in the middle. But if one is empty and one is occupied, then this first term is 0, and then you don't have hopping. Now, where did this model come from? So it turns out that this is an effective Hamiltonian in a particular limit of a very well understood model called the TV model. So this is a model where you have spinless particles, fermions, which can hop between neighboring sites, and there is a nearest neighbor density-density interaction with strength V. Now, this model is known to be exactly integrable, exactly solvable using the Bethe ansatz. So we know everything about this model that there is to know. But in a particular limit, where V goes to infinity compared to T, then you can see that the eigenvalues of this model will fall into disjoint clusters. Meaning there'll be a bunch of eigenvalues where you don't have two particles next to each other. So they'll all have eigenvalues of the order of T. Then there's a bunch of states in which only two particles are next to each other and nowhere else. So that those will have energies V plus factors of T. Then you can have two of these pairs, then you'll get 2V plus factors of T. So each cluster's eigenvalue is equal to an integer multiple of V plus terms of order T. And so now if you look at each of these clusters, you find that the effective Hamiltonian for this cluster is given by this equation. Okay, so that's by way of motivation of where this model came from. Okay, so it's just a particular limit of the TV model. Okay, so again, this is the Hamiltonian that I showed you earlier. If you look at it closely, you'll find that there are 3 local conserved quantities, one of which is really, really obvious, which is just the number of particles. But the other 2 are not as obvious, but you can show it easily. These are the number of nearest neighbor pairs on even numbered bonds and odd numbered bonds. So maybe I should show that actually. So think of this. So if 1101 goes to 1011, you can see the number of ones which are next to each other has not changed. So that's a conserved quantity, how many 11s are close to each other. Or if you go from 0100 then to 0010, again the number of nearest neighbor ones have not changed. But if you look at it even more closely, you'll find that the number of 11 on even numbered bonds is separately conserved and on odd numbered bonds is separately conserved. Okay, so those are the 3 conserved quantities, but these are some global quantities and these are not sufficient to explain the Hilbert space fragmentation in this model. Okay, so how do you show that this model has Hilbert space fragmentation? So it turns out that you can map this into a new model which whose sides lie on the bonds, which is dual to the original lattice. And we map between the two models as follows. So for a bond 0, 1 in the original model, in the new model it maps to 1. Or 1, 0 maps to 1, 0, 0 and 1, 1 map to 0. So of course this is a 2 to 1 mapping, right? So when you do a detailed counting, you have to keep this factor of 2 in mind. But apart from that, it's a very straightforward mapping. Now with this mapping, I thought there was something else in between. Yes. So these are the allowed processes in the original model, which involves 4 sites. But if you use this mapping in the new model, which has terms involving 3 sites, you find that you have processes involving only 3 sites. 1, 1, 0 going to 0, 1, 1. So this is called the diffusing dimer model, because basically 1, 1 is a dimer and it can go through a 0 from left to right. And this was studied long ago in a classical context. So they studied Markov processes involving transitions from these states to these states. And it considers particle number, of course. And this was studied in several papers by these people. But a really nice paper to read is this one in 1997. So in a sense, they were the first to really discover Hilbert space fragmentation. And then they use this idea of root states, which I'll tell you about. They found how many fragments there are and how many states are there in each fragment. It's a completely explicit formula that they have in their paper. In particular, if the system has L sites and L is very large, they showed that the number of fragments grows as the golden ratio to the power L. So tau is the golden ratio, root 5 plus 1 by 2. And the size of the largest fragment also grows as tau to the power L. They also showed that the model is integrable, which is not surprising because, as I said, it's related to the TV model by duality, and the TV model, of course, is integrable. But they showed that this model is integrable by a different technique. Now, this is a good point to introduce the idea of strong and weak Hilbert space fragmentation. So all the models we're looking at has a number of states which grows, total number of states grows as 2 to the power L because they're all spin-half models, or models where you have either 0 particles or 1 particle. So let's say the number of states in the largest fragment is D max. And let's say this also grows exponentially with L. So then there are 2 possibilities. If the ratio of the largest fragment size to the total number of states goes to 0 exponentially, it's called strong Hilbert space fragmentation. What it means is that even the largest fragment is exponentially smaller than the total Hilbert space. So the model that I just told you about shows strong Hilbert space fragmentation because the maximum fragment size grows as tau to the power L, total number of fragments goes to as 2 to the power L, and so this ratio goes to 0 exponentially. On the other hand, the ratio of D max to D total remains constant or goes to 0 only as a power of L. It's called weak Hilbert space fragmentation. So a typical model like a model of a magnet where magnetization is the only conserved quantity, there you have L sectors, right? Because the magnetization can take values from, let's say, minus L by 2 to L by 2. So the number of sectors is order L. And there, each of the sectors will have a size which is 2 to the power L divided by L. So there this ratio goes to, it goes to 0 only as 1 over L. So the standard model of, where you have just one conserved quantity is weak Hilbert space fragmentation. And if you have 2 global conserved quantities, it will go as 1 by L squared and so on. These are all examples of weak Hilbert space fragmentation. So strong Hilbert space fragmentation is the peculiar thing. That's the one that is most interesting and where you get very strange properties that I'll discuss. Okay, so that's strong and weak Hilbert space fragmentation. Are there any questions so far? I'm just going on. Yeah. Yeah, so we'll come to that. So it depends on which initial state, which fragment it belongs to, and so on. Yeah, so I'll come to that. Okay, so now finally I'll tell you about the model that we studied, the first model that we studied. So this is a model which is exactly the opposite of the previous model. So the previous model is where processes 1 and 4 are allowed. So just to be perverse, we studied a model where 1 and 4 are not allowed and 2 and 3 are allowed, just to see what happens. So this is a model where you can have hopping between 2 sites only if the neighboring sites are opposite. One is occupied, the other is not occupied. So only this and this are allowed. So the Hamiltonian is of this form, second and third. So you have hopping allowed between two sides only if their neighboring sides are one is 1, the other is 0, or 0 and 1. The previous one is where you had the hopping is allowed only if it's 0, 0, 1, 1. And here is the other way. Yeah, this is the Hamiltonian that describes that process. So you can see only if the neighboring sides are opposite, then this factor in front is 1, and then that hopping is allowed. So this is in this paper by Srimoy, Deepak. Okay, so again, so these are the processes allowed in this model. 1, 1, 0, 0 can go to 1, 0, 1, 0, or 0, 1, 0, 1 can go to 0, 0, 1, 1. So again, we use this idea of mapping this to a different model on the dual lattice. You map this 4-side process to a 3-side process. So you obtain now a 3-side model which only allows the process 0, 1, 0 to 1, 1, 1. Let me at least show this in one case. So if you do this mapping from the original lattice to the new lattice model, 1, 1 goes to 0, 1, 0 goes to 1, and 0, 0 goes to 0. So that's 0, 1, 0. And then this 1, 0 goes to 1, 0, 1 goes to 1, 1, 0 goes to 1. So it goes to 1, 1, 1. And for this 3-side problem, this is the Hamiltonian. Okay, so you can see that you can create particles or annihilate them in pairs. So what makes this model really difficult compared to the previous model is that you don't conserve particle number in this model. And basically for that reason, it's a much harder model to study. So there again some kinds of dual bond, number of bonds of certain kinds are conserved. But those are the global conserved quantities. So now I'll tell you about root states, which is actually the better way of studying the fragmentation in this model. By the way, this model also there is a kind of TV model from which you get this as a particular limit, but it's a very peculiar TV model. You have to take a model where the V's form a period 4 pattern, like plus V, minus V, minus V, the on-site V's, and then in the limit V going to infinity, you get this model. So it's a very artificial model, but it is actually the limit of some TV model, but which is not integrable because it has this period 4 structure. It's not translucent invariant. So, yeah. Okay, so now let me tell you how you look at the root state. So this is the key point in studying how many fragments there are. So you can, so the root states are things that we use to count the number of fragments and the sizes of different fragments. And it's easier to do this in this 3-side model. So this mapping to a 3-side model is not just a curiosity, it's really essential for analysis. Remember, this is the transition allowed in the 3-side model. 0, 1, 0 can go to 1, 1, 1. And we're going to consider open boundary conditions for convenience. Things get a little murky when you have periodic boundary conditions. Okay, so a root state is a unique state associated to each fragment, such that all the states in that fragment can be connected to the root state by a series of processes like this, 0, 1, 0, 1, 1, 1. Okay? So there is a fragment, it has lots of states in it, but all of them should be connected. It should be possible to connect all of them to one particular state. Now, there are of course many different ways of defining a root state, but so you have to pick a nice definition of a root state. So it goes as follows. So first of all, because of this transition rule, you can replace wherever you see a 0, 1, 0. So you have a string of zeros and ones. Wherever you see a 0, 1, 0, you can replace it by 1, 1, 1, right? Because they belong in the same fragment. The next thing to notice is that a string of 4 ones can pass through a 0 in either directions. So for example, if you have a 0 and then 4 ones, then by this transition rule, you can go to 0, 1, 0, 1, 0, right? You replace this last 1, 1 by 0, 1, 0. Then you can use this rule again and then map it to 1, 1, 1, 1, 0. So basically what has happened is that 4 ones are able to go through a 0. Now you combine these two, you can see that you can go from any state to a unique root state which has no 0, 1, 0s anywhere, because if you had a 0, 1, 0, you can just change it to 1, 1, 1. And it has no, and all the strings of 4 or more ones are only at the left end. So using this, you can move, whenever you see a string of 4 ones, you can move it to the left end of this system. It's open boundary condition. So that's a root state. Okay, so it has two properties, no 0, 1, 0s and strings of ones only at the left end. Then if you want, you can delete groups of 4 once. If there are 4, you just delete them. If there are 7, you delete 4 of them, you're only left with 3. If there are 8, you can delete all of them, and so on. This gives you an irreducible string because you can't make. So this actually reduces the size of your string. So that's why it's an irreducible string. So first, how many fragments are there? So the number of fragments is equal to the number of independent root states. Okay, so now, so there's a little bit of a pedantic thing here. So the question was, are there any conserved quantities in this? And there are only a few global conserved quantities, which has to do with how many dipoles there are. But Deepak insists that the root states are the conserved quantities. This is a very unusual kind of conserved quantity, but each root state basically corresponds to some conserved quantity because all the states in that fragment have the same value of the root state. Okay, so if you like, that's your conserved quantity. But you can see it's a highly non-local thing, right? It's not a global thing that you can easily count. I mean, given an arbitrary string of zeros and ones, it's very hard to see what root state it will go to. Yeah.
Is there a sense in which the root state change is This is not a particle number conserving.
This is not a particle number conserving. Yeah. But it's a good question. So I'll have something to say about that. So the number of fragments is equal to the number of independent root states. And you can count how many there are by defining an 8x8 transfer matrix. You find this is the minimum size you need for the transfer matrix. This has to encode the information that there are no occurrences of 0, 1, 0s or 4 1s, except maybe at the left end of the system. And so there's a unique transfer matrix. It's a very simple matrix. Every entry is either a 0 or a 1. And so we find then that this has the following eigenvalues: the tau, golden ratio, -1 over tau, plus minus I, and 0. The largest one in magnitude is tau. So the number of fragments grows exponentially is tau to the power L. Now the largest fragment. So this was actually the hardest calculation in this work. What is the largest fragment? So we actually so Srimoy did this numerical evaluation of various fragments, what are the sizes of them, how does it grow with the system size, and so on. And you find that the largest fragment of an L-side system is one in which the root state consists of L number of ones. So it can be 1, or it can be 1, 1, or 1, 1, 1, 1, and so on. No zeros anywhere. So let's say the number of states in fragments of the above type, which is only ones, is DL. So D0, we just take it to be 1 for convenience. Then you can show by explicit counting that D1 is 1, there is only one configuration which has a single 1. D2 is 1, D3 is 2 because you can either have 1, 0 or 1, 0 and 0, 0, something like that, and so on. So next you define a generating function which is a V of some complex number Z, which is the sum over L from 0 to infinity dl Z to the power L. So this is a standard thing to do when you're trying to find, when you're trying to solve a counting problem in combinatorics. Okay, now I'll skip over many months of effort. We found that this is the exact generating function for the largest fragment. So this is the key result in this paper. Very complicated object. Yeah. So if L is the number of states in the largest fragment for a system of size L, then DL, ZL, sum over L is the generating function. So DL is the number of states in the largest fragment of a system with L sides. Okay. So DL increases with L, and that's what we want to know. How does it increase with L when L is very large? Exact? G of Z is exact. Now this is a generating function. So what we did is we managed to find an analytical expression for this, which is there in the next slide. Did I use the word exact? I don't remember. Okay. I don't know where okay. This is the exact expression for V of Z. So you see, it's quite a complicated function. It has a branch cut and stuff like that. And so here's a key point about, sorry. Here's a key point about generating functions, that if you have a generating function as a function of some complex variable z, then the place where you have a non-analyticity of v of z, which is closest to the origin, that gives you the information about how fast this d of L grows with L. That non-analyticity can be anything. It can be a simple pole, double pole, it can be a branch cut, whatever it is. So if you stare at this, you'll find that the nearest singularity to the origin is where this square root thing inside the square root is 0. So that's where z is 1 over 12 to the 4th power, 1 over 4, 1 by 12 to the 1 by 4 power. And then you can show that, so the radius of convergence of v of z is 1 over 12 to the 1/4. And then this implies that this v of z grows as 12 to the power L by 4. And so that's 1.861 to the power L. So the size of the largest fragment goes exponentially as 1.861 to the power L. So you see, it's actually very different from the previous model that I told you about, where it grows as the golden ratio to the power of L. Yeah. Yes. Yes. Yeah. Oh, so this is the way we discovered V of Z. So so by looking at this, we found several symmetries, and they were really crucial for us to find V of Z. Sorry. It is exact, but to discover it, so this is a process of discovery, we notice some symmetries here. So let me give an example. For example, you see here that D7 is twice D6. And this pattern continues. D of 4k plus 3 is twice of D4k plus 2. So we found all these from generating these numbers. And using these, we discovered what V of Z has to be. But we found, this was just an aid to the discovery. The calculation had to do with finding this generating function by some recursion relations. Those recursion relations were exact. But if we didn't see this pattern, we would have had an extremely tough time finding those recursion relations to start with. Okay. I see. So that was no. So it is an exact result, but that was just an aid to discovering the exact result. Independent of? No. So V of Z is equal to this sum over dl zl. So what you do is that you take this thing and expand it as in powers of z. And the coefficients of z to the power L will tell you what the d of L's are. So when you expand this out, it's hard to believe, but when you expand this out, it does give you a power series with integer coefficients. Okay, and it's a very well-behaved power series, even though it looks like it has the square roots and stuff. It's a very nice power series. Okay, I just have 7 minutes. This is 7 minutes, including questions, I guess. Excluding questions. Okay. So that was the largest fragment. That was the toughest calculation. Then there are many other states. So there are things called frozen states, which contain only one state. So there are fragments which are only size 1. So these are states which don't contain any 0, 1, 0s or 1, 1, 1s. And the number of frozen states also grows exponentially like this. Then there are pairs of states which form a fragment. So there are fragments which have only 2 states each. And the effective Hamiltonian within these fragments is just a single Pauli matrix, just one Ising spin in a magnetic field. Okay, so let me skip all this. So let me now tell you about some static consequences of Hilbert space fragmentation. So now for this study, it's better to go back to the foresight model. So that's what we look. Let me go back to that. And so we take a system with open boundary conditions, divide it into 2 equal halves, and look at the entanglement entropy between those 2 halves. Okay, so it's described here, but I'll skip over that. So this is what your half chain entanglement entropy versus the energy for different eigenstates looks like. So you notice that you actually cover a region. So there's a kind of rainbow. The upper envelope is kind of a rainbow kind of thing, and then states inside are filled up. And they get more and more filled up as you go to larger system sizes. So essentially, this entire thing is filled up when you go to really large system sizes. Now, this is the same pictures as in the previous slide. Now, on the other hand, for a fully ergodic system, you're not supposed to get a picture like this. You're just supposed to get a single curve. Okay? So the reason you have this filled up region is that this is the signature of Hilbert space fragmentation. So what is happening is that the system consists of many fragments. Each fragment has its own rainbow thing, but these rainbows are all different from each other. So when you combine all of them, you get a filled up region. So that's the reason for this kind of a pattern. So the full Hilbert space has this particular picture of S versus E, whereas if you look at just the largest fragment, that has a picture like this. Okay, so the largest fragment is a non-integrable ergodic system on its own, and it has a standard thermal kind of S versus E rainbow pattern. Now there are outlying states, and these are scars and things like that. Okay, but most of the states are follow this nice rainbow pattern. Similarly, if you look at the distribution of energy level spacings, if you do this for the entire system, all the states, you get a Poisson distribution. So I'm sort of running out of time. So this is the standard level spacing ratio of spacings between neighboring energy levels. You get a Poisson distribution, and that's because you have all these different fragments, and they are sort of behaving like the different sectors of an integrable system. And for an integrable system, it's supposed to have a Poisson distribution. On the other hand, if you just look at the largest sector by itself, you get a Gaussian orthogonal ensemble. So once again, the full system is behaving like it has a large number of conserved sectors, but the largest sector by itself behaves like a single non-integrable ergodic system.
This is weak Hilbert space fragmentation. This is weak Hilbert space fragmentation.
This is weak Hilbert space fragmentation. Wait a second. No. So no, it's not. No, because the definition that I had is the size of the largest fragment to the full Hilbert space. That goes to 0 exponentially. Because the largest system size was 1.861, right, to the power L. This was the largest fragment, which is exponentially smaller than 2 to the power L. So this is strong Hilbert space fragmentation. But within the largest fragment, it is kind of weak ETH because there are these outlying states. So all the states, even in the largest fragment, are not thermal. Some of them are very atypical. So it's weak Hilbert. So the way to say it, I wouldn't say weak Hilbert space fragmentation is weak ETH, a weak version of ETH. So not all states. Right. I think I'll skip over the autocorrelation function because I really want to get onto the next model. So the existence of these frozen states and many other states basically shows that ETH is not satisfied in the full Hilbert space. So this is what you were saying. But it is satisfied within sufficiently large fragments. And so this led us to this concept of subspace restricted ETHs. So in each fragment, if it's sufficiently large, you have an ETH. So it's restricted to subspaces, but it's weak ETH because of these outlying states. Very quickly, our second model of Hilbert space fragmentation. So I really won't have time to discuss this, but it's a model where only the second and fourth processes are allowed. So these are processes where you can hop between two sites only if the site to the left of them is occupied. It doesn't care what the site on the right is. It can be occupied or unoccupied. So it's called the East model for some reason. This East is not anyone's name. It's like East, West, North, South. You could have equally well called it the West model. In 2 dimensions, you can have North models, Northeast models, whatever. It turns out this has a very different behavior from the previous model because it violates parity symmetry and particle hole symmetry also. So this is discussed in this paper with Maitri Srimohi. Okay, I'm just skipping over all this because I'm really running out of time. This model has scars. Okay, so let me just go to the summary and then I can take questions. So we studied 2 one-dimensional models which show Hilbert space fragmentation. In both of them, the hopping between 2 neighboring sites depends on the occupancies on the sites to the left and right of them. And we found the number of fragments using transfer matrix methods. This was quite complicated in the first model. But in the second model, the yeast model is actually turned out to be simple. The sizes of the fragments turn out to be something called the Catalan numbers, or Catalan triangle, which is a generalization of Catalan numbers. So we found it exactly. We studied the distribution of energy levels, half-chain entanglement, and so on. In both models, ETH is generally not satisfied in the full Hilbert space, but it seems to be valid in the sufficiently large fragments. So it's kind of a subspace restricted ETH. The yeast model has a new property which I didn't have time to tell you about, that it has a transition between strong and weak Hilbert space fragmentation. So above half filling, it has weak Hilbert space fragmentation, and below half filling, it has strong Hilbert space fragmentation. So that's a peculiarity of that model. The yeast model also has some many-body scars, which we could find exactly. And the Loschmidt-Echo, which I didn't define, it's basically you start with an initial state and evolve it according to the Hamiltonian and see its overlap with itself after a long time. And it shows oscillations, but it has completely different long-time behaviors depending on whether the initial state has overlap, large overlap or not with the scar states. Okay, so let me stop there. So these are pictures of my collaborators. And these are the references and the funding. Thank you.
Questions? Maybe I can begin.
Yeah.
So the yeast model, you said, has a transition at half filling, but
yeah,
is it only at half filling? Because I would think that above half filling and below half filling should be symmetric.
It's not, because it doesn't have particle hole symmetry. So let me show you the Hamiltonian of the yeast model. This is the Hamiltonian of the yeast model. So you can have hopping between J and J plus 1 only if J minus 1 is filled. So you can see it doesn't have this n going to 1 minus n symmetry. So it doesn't have particle hole symmetry. So that's why it can have different behaviors below half filling and above half filling. And we could show that there's this transition because we know exactly the number of states in the different fragments given by this Catalan triangle, and then we use Stirling's formula to find the number of states in the largest fragments. And we basically find that this ratio, size of the largest fragment to the total size, it goes to 0 exponentially if you're below half filling and goes to 0 only as a power law of L above half filling. Yeah.
Yeah, so just to understand, so it's a little bit, just to understand the basic notion of the fragmentation. So it's a little bit like having an integrable model, but the number of conserved quantities is not equal to the number of sites, but some kind of reduced fraction of the number of sites, right?
Actually, I would say its number of conserved quantities is exponentially large in the number of sites, because it's like saying every fragment corresponds to a different value of some conserved quantity. That's one way of looking at it. But I think it's, I mean, my viewpoint is that, it basically has no conserved quantities. But Deepak would say that every fragment is a different conserved quantity. Anyway, there is no global conserved quantity in this model. Right? Apart from some trivial ones like the total number of particles, there is no global conserved quantity.
So is an integrable model just sort of an extreme limit of fragmentation, and this is some kind of partial sort of not complete integrability?
No, not really. So the first model that we talked about, which is not number conserving, that is actually not integrable in the largest fragment. It has small fragments with 1 or 2 states which is integrable. But the largest fragment in that model is not integrable at all. So it's not integrable in any limit, actually. And there is actually, there's no parameter you can vary. The only parameter is the hopping. That's the only parameter in this model. So there's nothing you can vary to get to an integrable point or away from an integral point.
Are there examples of this in higher dimensions?
Sorry?
In higher dimension than 1, are there examples of this fragmentation?
Yeah, so the experiment was a higher dimensional example of a square lattice with a tilted potential, the Bose-Hubbard model on a tilted potential. That was an example of a higher dimensional non-integrable model which shows Hilbert space fragmentation. But Yeah, it's hard to do a good analysis of higher dimensional models. So like find how many fragments there are, what is the size of the largest fragment. I don't know if there are any examples in more than one dimension.
Is there anything interesting if you add unconstrained hopping to this? So add some ordinary C-dagger C-type hopping?
Yeah, then you'll probably destroy Hilbert space fragmentation. So Hilbert space fragmentation is not very robust. There are lots of terms which will just immediately destroy it as soon as you add them to the Hamiltonian. Yeah. So I think if you had just add an unconstrained hopping, I think that would just destroy Hilbert space fragmentation. But it's a good question if you add a small perturbation which destroys fragmentation, then you let it evolve in time, then you probably have very long times, pre-thermalization times,
You mean like
before the entire system thermalizes.
You mean like a local perturbation?
Yeah, like an unconstrained hopping. If you add a small term like that, it will destroy the fragmentation, but then you have an interesting question of what is the time scale over which it destroys the fragmentation. So we have not studied that.
Any other question? If not, let's thank Diptiman.
Thank you.